I know a lot of people put the new homework scheme.
What I'm thinking is this here. Not in Excel, in that table. Stop thinking about it.
Oh, you already split it?
Yeah. And Dan, can you put the electronic version of this on the web as well? And you call this 5, whereas this is, or you call this lab assignment 1.
Yeah, I call that lab.
What is the first? Nope. Oh. Just using standard.
Okay. Let me start with a few announcements. Let's see. Homework is due today. That's the lab assignment 1. Pick up the solution on your way out. That's this stack here. Pick up homework number 5 handout. It's 1 page. And it consists of 2 handwritten problems off of Oppenheimer and Schaefer 5.43 and 5.57. And then it has 2 lab assignments. For which you need some input, and the thing called prop3.mat file, and that's on our website. And this is due next Friday, okay, October 17th. Midterm is Wednesday, October 22nd. It's in Sibley Auditorium, and it covers through homework number 5. That means through the one that you hand in next time. Okay, we call this homework number 5, and we call what you hand in today lab number 1. But I think it's just a matter of how you name things. So it covers through this homework that you hand in. That means it includes FIR window design technique, but it sort of just ends there. So even if on Wednesday and Friday next week I'll be lecturing on, I don't know, optimum FIR filter design, because you haven't done any homework on that, that won't be covered in the midterm. And as I said last time, you can bring in one sheet of formula or whatever you want. It can be two-sided. You can write it as small as you want. For the final, which will also be just an hour and a half, you can also bring one sheet. I'm sorry, we can bring an additional sheet if you want, a total of two. You can either reuse the one from the midterm or just make two new ones, etc. And finally, don't forget to pick up your graded homework. That's this pile over here. Before I start lecturing, I would like to get a quick show of hand as to how long it took you guys to do the lab, just so that I'm calibrated. How many people took less than 5?
5 days around.
Okay. We'll get to you. Oh, that tells me how far out I have to go. How many between 5 and 10 hours? And how many between 10 and 15? And how many between 15 and 20? How many 15 and higher? Okay. And for 15 and higher, did you use MATLAB before? Had you used MATLAB before? It's your first time. Okay. And how about you? Had you used MATLAB before? In 120? Okay. How many? Yeah. Okay. All right. Let's see. Let me pause right now. Are there any questions or comments? Is how many people actually use the machines in Cori for the course rather than, I don't know, your own laptop or your own computer at home? How many people use Cori facilities? A number. Okay. Okay. Are there any comments or questions, either regarding the lecture or homework or something like that? Yeah.
The final exam is going to be comprehensive? Or
Yeah. Yeah, it's comprehensive. Yeah. So the midterm covers from the material from the beginning of the class to here, and the final is the entire thing with slightly more emphasis on the latter half, because that's because you didn't get tested on that. It's not actually, one thing I got to say, we don't have a final exam per se, even though they might have announced the final exam for the course. It's going to be in class, the last lecture of the semester, as I said in the information sheet at the beginning of the class. The last lecture of the semester, it will be the final. It will probably be in Sibley, I'm not sure. Dan, is it in Sibley? Yeah, I might make a reservation for that in Sibley, or it could potentially be this room and next room. Okay? So, if there are no other questions, I want to get going on the lecture. So, what we talked about last time was filter design, okay? And in particular, what we talked about was FIR filter design using the window technique. So the main idea there was that you have some sort of an ideal filter in mind. It could be an ideal high pass, an ideal low pass, and an ideal could be whatever your ideal is. You know, I don't have to tell you. For most people, it's something that looks like a box, either a box like high pass filter, or a box like low pass filter, or a box like band pass or band stop. Because everybody wants to have infinitely sharp cutoff. So we talked about one way of doing it is you start with the idea, you compute the inverse discrete time Fourier transform, you get the ideal impulse response, and most times that's infinitely long. And what you do, so the unfortunate thing is that the ideal impulse responses, they're not only infinite long, but they're also don't correspond to rational transfer functions, so you can't really implement them with difference equations. So to make him FIR, you have to somehow truncate it. And it's over there. And to truncate things, you can either multiply it by, either just chop things off, which is equivalent to multiplying by a rectangular window, or you can multiply by other fancy windows, and that's really the topic of today's lecture, is designing FIR filters using the window technique. And so where we left things last time, just so that you remember, was this page which said, if you multiply by let's say a rectangular window of duration 2n0, then it's in the frequency domain. It corresponds to convolving the Fourier transform of the ideal response with Fourier transform of the window, and Fourier transform by this window, rectangular window, is the sink. And the width of the main lobe here is inversely proportional to n0. So the longer the duration of the window is, the narrower this width of the main lobe is. And in the limit, when this window becomes infinitely long, this thing approaches to a delta function, which means you're convolving with a delta function, which means the ideal impulse response is the same as the actual impulse response you end up getting. So what I'm going to talk about today is a little bit more on this issue of how does the window function affect the final frequency response you get. Before I start writing, actually, I just wanted to make like one little practical comment. So all of what I'm talking about is really digital filters. And in this day and age, there's no course on analog filters. But I just wanted to make a little comment. If we're not going to make digital filters, what are some ways one can make analog filters? What are some analog filters you've ever used or built or touched or implemented or anything like that? Anybody ever did anything in that? Yeah.
I think I once built an RC circuit in ED40.
An RC circuit. And for mechanical engineering students, R stands for resistor and C stands for capacitor. So the resistors and capacitors. So that's a low pass that you can build analog filters. And how, if you're in the analog domain, how else can you build filters, analog filters? I mean, even if you didn't build it yourself, just have you heard other engineers talk about building analog filters? Actually, in this case, mechanical engineers should really. Do we have any mechanical engineers in the course? Raise your hands. Oh my God, they all disappeared. Yeah, you guys should know. I mean, what else would we use to do analog filtering? There's this book by a fellow by the name of Lamb. When I was an undergraduate, that would be the textbook you use for analog filter design. But they don't, as I said, they don't teach that anymore.
I think I was in OPM.
Exactly. Good. That's exactly what I wanted you to say. Op-amps, right? You can use op-amps that are made of transistors. You can also make analog filters out of transistors, but nowadays people have packaged a whole lot of transistors into one thing that's called op-amp. And what's the classic op-amp everybody uses? 741. And who makes that? National. I think it's National, isn't it? Anyway, one of those companies make it. But anyway, 741 is the classic op-amp. It's been around for 30, 40 years. You put some resistors and capacitors around it, and you can build all kinds of nicely shaped analog filters. Again, we don't talk about that. We do talk a little bit about analog filters when we talk about IIR filter design, because one of the methods of designing IIR filters is to borrow ideas from analog filter design or continuous time filter design. And one last thing, besides electronic analog filters, what other kind of filter can we talk about? What other kind of filter is there? Higher frequency than electronics is what? Optical filters, right? Like you get your camera, you can open it wide open, and there's filters there. And you can, in the optical domain, you can have filters that just pass one frequency. It's sort of like a film. Or you can have filters that are low pass, and you can have filters that are high pass, etc. And if you're just passing one frequency, typically what you use is organic molecules that are found in nature to pass certain frequencies. So if you want to have a really sharp cutoff, or cue, if you will, you can't pick any arbitrary frequency at random. You have to sort of pick the ones that are available that allow you to pass light. So one of the projects, for example, right now I'm involved in, we're trying to, it has to do with dynamic scene visualization. And what we want to do is we want to have, there's a famous technique in computer vision where you put pattern or structured light on an object. And then using triangulation techniques, you can recover depth. The problem with that technique is that the human eye sees this pattern, this visible pattern in the visible domain, and that's highly disruptive. So what we're trying to do is do it in the infrared domain. And to do it in the infrared domain, it turns out that if you take a typical light bulb and you look at its spectrum, actually only 2% of the energy of a light bulb comes in the visible domain that we see and we use. 98% of it is wasted where? In infrared. So it's already a good source. And so if you can just sort of use filters that block visible or block infrared, depending on what you want to do, optical filters I'm talking about, which are just a little piece of film like that, then you can do a lot of interesting image processing and signal processing. So I just wanted to take a little sort of detour in that because not every filter in the universe is digital. You still have to use some optical stuff that at very, very, very high frequencies that you just can't do things in a digital fashion. Besides, in optics, you can use lenses to do what? Fourier transforms. You start with the image, you pass it through a lens, the Fourier transform comes out. So there's, in nature, there's natural ways of doing Fourier transforms. Another example where Fourier transform pops up is, and this week somebody in England got Nobel Prize for it, is Mansfield in England got a Nobel Prize on MRI signal processing. There were two of them. I forgot, Latimer or Latimer, how do you pronounce one of the guys was at University of Illinois, and he invented the principles where how MRI works. And then his counterpart in Britain, he figured out the mathematics of the signal processing of MRI. And the reason I'm bringing it up is that that's another arena where Fourier transforms automatically arise. That sampled signal that you get off of the MRI machine is the Fourier transform of the hydrogen density of the slice that you're looking for. So nature comes up. There's many situations in which the things that you observe are already Fourier transform of something else that you want to get. And nature certainly didn't know about e to the j 2 pi nk over n's or e to the j omega n's. So what I'm trying to say is that Fourier transform occurs in many natural systems just by itself. It occurs also in synthetic aperture radar. Turns out when you take the synthetic aperture signal, if you want to get the height map of what you're looking at, you also do an inverse Fourier transform. So it pops out lots of different places naturally. Okay, so that's the little detour from the main topic I was going to cover, and that is that there's besides the digital filters that I'm teaching you how to design, and we spent a lot of time talking last lecture how to implement, there's also lots of analog filters and optical filters and other ways of filtering signals, depending upon what frequencies they are at. Okay? So let me get going on filter design using FR filter design using Windows. Okay, so just as a review, the basic idea was you start with a ideal filter, H sub d of omega. You take inverse DTFT to get H sub d of n, and then you multiply by some window to get h of n is equal to h sub d of n times w of n. And so what I want to show now, what I want to start with is talk about filter specifications, just so that I can talk about this window design. It becomes clear why I do that. Typically, when you have, remember, the goal of designing a filter is to come up with tap coefficients so that they satisfy some sort of a spec. And so typically when people come up with specification, we have already done a little example in the last lecture, is that you look at h of omega and somebody tells you, look, it's going to be, first you specify what kind of filter it is. In this case, we're saying it's low pass, for example. Then you have to specify what the passband frequency is. So we're going to pass the frequencies between 0 and omega p. And then you have to specify the stop band frequency. So this is called passband. And then you're going to have to say from some other frequency, omega s onwards all the way to pi, we're going to stop a bunch of frequencies. And this is referred to as like the stop band frequency, stop band. Okay. And again, in an ideal filter, the distance between omega p and omega s is 0. They're the same number, right? That's ideal when you want to have brick coming down. But that brick thing has a infinitely long impulse response that doesn't even have a rational transfer function. But that's really in fantasy, not reality. But also, you want to have to specify what values you want your filter to take. If it is low pass, ideally you want it to be smack 1 here and smack 0 here. But in reality, you can't really get smack 1 and smack 0. So what do you get? You get ripples and variations. So you specify a band around 1. So you say, look, it can be from anywhere between, magnitude of it can be anywhere between 1 and 1 minus delta p. And if I remove the magnitude, it would be between 1 minus delta p and 1 plus delta p. But let's just talk about magnitude. And when I paint it like this, I'm just trying to say that magnitude of h of omega can take on any value in this range, but as long as it doesn't come out of this box or exceed this box, then we're okay. And then there's the transition width. Here at this other end also, we would like it ideally to be smack at 0, but it's not. And so what it is some other small ripple, delta sub s. Okay? So this thing here, from here to here, which is called delta s minus omega, omega sub s minus omega sub p is called delta of omega, and it's referred to as transition width. And delta sub p, and so let me write down all the notation that sort of goes with it. So the frequency range between omega p and 0 is called passband. The frequency range between pi and omega s is called the stop band. And delta sub p is referred to as passband ripple. And delta sub s is referred to as the stop band ripple. And delta omega, defined by delta omega s minus omega p, is called transition width. Okay? So that's typically a sort of specs that you end up getting. Now, having said that, let's go back to our window-based design technique, and let's draw some pictures to see how the frequency response of this filter that we end up getting relates to the frequency response of the original desired filter as a function of what the window function does. So if I were to plot some of these things, here's what I would get. So suppose that as a function of omega, my h sub d of omega looked something like this. Okay, it's some sort of a box function. And suppose that I have a Fourier transform of W of n, a discrete time Fourier transform of W of n. I refer to that as W of omega. And suppose that W of omega, magnitude of W of omega, look like this. Something like that, okay? And it's if W was a rectangular window, W of omega would be a sink, and it would go up and down. But because I'm plotting the magnitude, that's why it's doing that. So what I said last time, the way we ended last time's lecture, was that H of omega is just H sub d of omega convolved with W of omega. So if I were to convolve these two things, what sort of a picture would I end up getting? Well, what does convolution means? First, I have to flip this guy over. Oh, but in this case, I've plotted it symmetrically, so flipping doesn't matter. Then I drag it all the way to this side, and then I pretend I have a string, and I drag it like a train. And at each location, this gets multiplied by that, and I add it up. So let me use multiple colors to demonstrate that. So essentially what's going to happen, let's say, is when this guy is at this location, so I end up multiplying this red thing by this black thing here, and then adding it all up, and that gives me the value at this location. And so what value do I get? At far out, when this blah here is far out here, what value do I get as the result of convolution? Some small thing. It's not exactly 0. Why is it not exactly 0? Because of these guys. Because this is called the main lobe of it, and this is called the side lobes of the Fourier transform of the window. Because these side lobes are not exactly 0. They're non-zero. So you get a little bit of blah, let's say here. And at what point do I start getting, as I pretend I have a string attached to this, and I drag this red thing like that, right? At what point do I start getting some significant contribution? Yeah, that's right. When this big peak starts reaching here. So at one point it starts overlapping here. Then as soon as it starts overlapping here, then I start getting sort of right around here, I start getting some, no, actually right around before even, so before even I hit this amount. So if the width of this thing is, let's call it some notation, delta omega naught or something like that. So if the width of this is delta omega naught, so if I bring that all the way down here, delta omega naught before I hit this guy, I start having non-zero contributions because this starts overlapping with that, and boom, this starts going up. And finally, this blah here, when it reaches here, from the point the center of this blah is here, all the way to the point where the center of the blah is here, I'm going to get more or less constant, assuming that this is constant. I'm going to get more or less constant with some variations across it. Why do I have variations? Again, because there's blahs coming in, and there's ripples coming in, getting multiplied, etc. And then it gradually comes down here, and then I go to 0. Okay? So the reason I drew this picture like this, and I was meticulous about saying how this convolution works, is because I want to label this thing. So this is the resulting H of omega, magnitude of H of omega that I end up getting. So does the resulting H of omega have an infinitely sharp transition from 0 to 1? No. It has, again, because this thing has non-zero width, this thing does not have infinitely sharp transition. It has a transition width. And what is this transition width proportional to? What affects what the width of this transition is? Yeah, the width of this main lobe, right? The fatter this guy is, the longer it takes for this thing to go from 0 to 1, right? Just because of the way convolution works. So what I'm trying to say is that the transition width of the final filter of h of omega depends on the main lobe width of the filter. Okay, this is called the main lobe width. So this filter has got what's called the main lobe, that's the main lobe, and it's got these guys that are called the side lobe. Okay, not lobe, but side lobe. Okay, so the transition width of h of omega depends on the main lobe width of the filter. And what else can I say? Depends on, or we can say proportional. It doesn't matter. What else can I say? How about the junk here and the junk, I mean the ripple here and the ripple there and the ripple there? What does that depend on? It depends how high and how prominent these side lobes are. If the side lobes are very high, let's say the side lobe came all the way here, 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 etc., way even before I get here, I start having contributions. Okay, so the ripple here and the ripple there, ripple in the pass band and in the stop band depends on the side lobe width of the window. Why did I say a filter? Window. So the ripple in pass band and stop band is proportional to the side lobes of the window. And by side lobes of the window, I really mean the Fourier transform of the window, because we're not all in the Fourier domain. Okay? So once again, ideally speaking, I want the main lobe of the window to be as narrow as possible, and I want the side lobes of the window to be as little as possible. And what would be something in the fantasy world that satisfies that? Yeah, a delta function. That means if W of omega was a delta, which means the window was of infinite duration, but that's fantasy world, okay? So the question that I want to ask is, how do we design the window function W of n in order to get good, and I put good in quotes, good main lobe and side lobe behavior? So that's sort of what we're going to concern ourselves with. So the question is, how to design the window W of n to get good main lobe / side lobe behavior, or properties, or whatever you want to call it. And so I'm going to decompose that into two parts. Question one, how to get good, how to control main lobe width. And what do you think is the easiest way of controlling the main lobe width? It's the duration of the window, okay, or the size of the window. The answer is, it's the size of the window, okay? And why does that come about? I mean, you already know for rectangular window, the longer the window is in the time domain, the narrower it is in the Fourier transform of it in the frequency domain. But there's a deeper reason. There's a deeper reason behind that. And what is that? That doesn't just hold true for rectangular window. It holds true for a whole lot of other windows and a whole lot of other functions. And what thing tells you that that's true?
If the window is very wide, then it covers a lot of components of the city.
Uh-huh.
So it presents the characteristics.
Uh-huh. I mean, we already talked about it just a little bit. Is that all I'm saying is the longer the window is, the narrower in time domain, the narrower it is in frequency domain. What property is that?
The duality between frequency and time is stretching time to compress frequency, and vice versa.
Yeah, there is a duality, but why is that true? What's that called? It's a word I'm looking for. Yeah, whoever said, I didn't know who said it, but that's right. It's uncertainty principle, which there's an equivalent of that in physics. And what does uncertainty principle in physics say? can't hear you. Who said it? It's okay, Kevin, say it.
Isn't it you can't predict the location of electrons with respect to something? You can't know two things at once.
Right, you can't, in physics, that's almost correct. It's in physics, it says you can know where a particle is and how fast it's moving arbitrarily accurately. You can either know precisely where it is and not know how fast it's moving, or know precisely how fast it's moving but not know where it is. So the uncertainty principle in physics says the product of the uncertainty in the location of a particle and the speed of it is constant. You can either know one variable or the other, or there's a trade-off between the two. And in signals and systems, there's also a thing called uncertainty principle, which just says, roughly speaking, the width of signals in time domain and the width of their Fourier transform, the product of the width of a signal in time domain and the Fourier domain is roughly constant. You can't have arbitrarily narrow signals in time and simultaneously narrow Fourier transforms for them. And that's what uncertainty principle says, and that's really the guts behind this. Okay, so size of the window. So by increasing the size of the window, you can control the main lobe width. So that comes from uncertainty principle. Okay, and for example, again, we come back to the thing we know a lot about for the rectangular window. What we end up getting is of length minus m to m. The magnitude of W of omega is going to be, it's going to have a main lobe width here, delta of omega, which goes from minus 2 pi over m plus 1 to plus 2 pi over m plus 1. Okay? So if I make m larger, this becomes smaller. And so delta omega, the transition width here, is 4 pi over m plus 1. And how about the shape of the window? That also affects, so the answer to question 1 is both the size of the window and the shape of the window. Now, if I fix the size of the window but change the shape of it, I can get different main lobe behavior. So fixed size windows but different shape have different main lobe behavior. Different main lobe widths. And just to quantify that, I want to show a table off of Oppenheim and Schaefer. And that's on page, let's see if I can. Yeah, right here on page figure, let's see, 722. So look at figure 722, Oppenheimer and Schaefer. And here's examples of a variety of windows. But before I show you their Fourier transform, can you zoom up just a tiny bit? I want to show you what the filters are. So what you see here is the rectangular window shown by this thing. And then there's the Hamming window, which is the black curve that you see here. Then there's Hamming window. Then there is Blackman window, and then there's Bartlett window. So different kinds. The Bartlett window is the most straightforward of the all. It's just a straight line from here to here, and then another straight line coming down. And the Hamming, the mathematical equations for those are written here. This is rectangular. That's Bartlett. This is Hamming. It's got a raised cosine. You got Hamming, a slight variation of the raised cosine. And then you got Blackman, which is the sum of two cosines. So those are the mathematical equations for those. But now, just to show you that depending upon what the shape is, you get different main lobe behavior. So what we're plotting here is a 50-point window for these different functions. So what I have up here is just a rectangular window. This is the magnitude of the Fourier transform for a rectangular window, and I'm plotting it in dBs. So it's 20 log 10 of magnitude of Fourier transform of the rectangular window. And as you can see, the main lobe width is pretty tiny. It's less than So if this is 0, this is 0.2 pi, this middle point is 0.1 pi, I would say it's less than 0.05 pi or something like that, maybe 0.03 pi or something. Now move down here, this is the same thing but for Bartlett window. So what has happened? The main lobe width has increased or decreased? Increased. Then I move down here, this is Bartlett and this one is Hanning. These are probably approximately the same, not too different. Then you move on to Hanning, slight increase over Hamming, and then you move on to Blackman, and Blackman has the highest main lobe width. So even though they're all 50 points, the shape of the window affects the width of the main lobe. And if you wanted to look at a precise relationship, it's shown here, again for a 50-point filter, or let's say a filter of, a window of length m. So rectangular has the approximate main lobe width of 4 pi over m plus 1, where m is the duration of the window. Bartlett is 8 pi over m, so twice as fat main lobe. Hanning is 8 pi over m, Hamming is 8 pi over m, and Blackman is 12 pi over, and it really becomes a whopping thing. Okay? However, while we're at this picture, there's another interesting phenomenon going on. And what is that phenomenon? If you can zoom out just a little bit. If you look at the succession of the filters, this is rectangular, this is Bartlett, this is Hanning, and this is Hamming. What besides the fact that the main lobes getting fatter as you go down this way, what other thing happens? The side lobes are coming down also. For example, if you again zoom in the rectangular window, the peak side lobe for a rectangular window is above minus 20 dB. I don't know, it's about minus 13 dB or so. By the time I move here, the peak side lobes is minus 25 dB. It's below minus 20, so that's about minus 25. And the peak side lobe here is minus 31 dB. Move down here, it becomes somewhere around here, minus 41 dB. Here, the first side lobe is not the highest one, but rather this one is the highest one. And when I go to Blackman, the peak side lobe is fantastic. It's minus 57 dB. Okay? So whereas the Blackman filter has higher main lobe width, and it makes you suffer as far as transition is concerned, it has such low side lobes, and therefore it's going to have lower ripple. Okay? So the thing I want to convey here is that the shape of the window has an effect both on the side lobe and on the main lobe. Okay, so that answers our question 1, and question 2, which we already sort of answered, is how to control the side lobes height, and the answer is primarily through shape. It's through the shape of the window. Okay, it turns out that changing the duration doesn't affect the height of the side lobe that much. Okay. And if you zoom back here, what you see is again, this is the peak side lobes as it goes down. This table doesn't really show it, but I can look somewhere else here. You can show numerically, for example, this is for Kaiser window that I just come to it in just a second. You can show empirically through numerical simulations that if you change m, the duration of the window, that really doesn't affect the side lobe height. It primarily has an effect on main lobe width. Okay, so putting together these two questions, with sort of conclusion that we get from these two questions is as follows: is that the shape affects both side lobe and main lobe, whereas the size of the window only affects the main lobe width. It doesn't have any effect on the side lobe width. Okay, so you have one knob that controls two things and another knob that controls just one thing. And so what would be, based on this observation, what's a good strategy in order to design our window function? Well, we know the only way to affect the side lobes is through shape. So we might as well choose the shape to be in such a way that it does something useful to our side lobe. So then the strategy is just to choose the shape to affect the side lobe and then to choose the size to affect the main lobe. Because if you do it the other way, you'll have no control over the side lobe. So the strategy would be use shape, or choose the shape to control side lobe behavior, which in effect controls ripple in the final filter, and then use the size parameter or knob, or choose, whichever one you want to use, to control the main lobe behavior. And this main lobe behavior affects the transition width. Remember, in the ideal world, none of these things matter. Transition width ideally should be 0, ripple ideally should be 0, but in real world, none of these things hold true. So it turns out that besides these, there was a time in the 70s that in the signal processing community, the quickest way of becoming famous would have been for you to design a window based on your name, and then you quickly, like this guy Hamming and Hanning and Blackman. So it turned out that sort of Kaiser, not Kaiser Permanente, the insurance guy, but a fellow by the name of Kaiser came up with a thing called Kaiser window that put an end to the window design game. Okay, and the way he did that is pretty straightforward. He came up with a parameterized set of windows where you have two parameters, then you can do all these trade-offs in a nice systematic way. And what do I mean by that? Well, he came up with the following shape for his window, and this time don't ask me how he came up with it because it's pretty weird. So it's I naught of let's see, beta prime of 1 minus n minus alpha over alpha squared, and then this whole thing to the power of 1/2 over I naught of beta prime, where n is between m and 0, and the duration of the filter is obviously m plus 1, and it's 0 otherwise. And so you're going to quickly ask me, what are these I naughts and betas and beta primes and stuff like that? Well, I naught is just a 0th order modified Bessel function. 0th order modified Bessel function. And you still might say, well, what's that? Well, there's two different ways of arriving at Bessel functions. Can anybody say what those two ways are? Has anybody seen Bessel functions before? So, yeah, I think you're on the right track. So what is it?
Exponentially decreasing size.
Yeah, but generally speaking, how does one go about defining functions? Like the CRC book, remember that none of you had seen, but now you all know what it is? Because like in CRC book, what do we look up? Like cosine, sine, those, what's the definition of cosines and sines? Besides that, if you have a right angle triangle, it's the ratio of this to that and all that. And an alternate way of defining cosine and sine and exponentials and logs is series expansion. Good. So let's define I naught of x as a series expansion. It's 1 plus x squared 2 to the power of 2, 1 factorial squared plus x to the 4, 2 to the 4, 2 factorial squared plus, etc., x to the 6, 2 to the 6, 3 factorial squared, etc. Or another way of defining a Bessel function is what? That I expect not too many of you to know it. It's a solution to a particular differential equation. Okay, so it's a solution to the following differential equation. And it's x squared dy squared dx squared plus x dy dx minus x squared plus n squared y equals 0. And is this a linear constant coefficient differential equation? No, absolutely not. It's a hard differential equation. It's the kind of thing they teach you in maybe junior or senior level math classes, but it probably also has a name. But n here defines the order of it, okay? So in this case, I'm talking about 0th order modified Bessel function. So n is equal to 0. You can have first order modified Bessel function, second order, third order, etc. Okay? And you might say, well, what's alpha in this whole thing? Well, it turns out that alpha is just, well, let me continue going down this way instead of writing in the corners. Can you make sure this is in this way? Thank you. So alpha is the same as m plus 1. I'm sorry, alpha is the same as m, where m plus 1 is the number of taps. And I apologize if this alpha sounds and smells like the same alpha as we had for linear phase. It's not. That other linear phase alpha, remember the slope of phase as a function of omega, this alpha is not the same as that. And then beta prime is, it affects the shape. So alpha is the, we can even call this alpha prime. Let's just do that for completeness. So let's call it alpha prime is equal to m, and m plus 1 is the number of taps, how many non-zero coefficients we have. And then beta prime affects the shape. So as you tweak beta prime, you trade off main lobe width with side lobe width. So it's a way of trading off main lobe width with side lobe width. Okay? So let me just show some pictures here so that you know what this thing is all about. If you can just zoom in this top picture. And what we're showing here is figure 724. I write that down in the notes because the notes get posted on the web, and people who are watching it at home, or if you're watching it later, you want to know what figure we're looking at. So what we have here is the shape of the Kaiser window as a function of this parameter, which I call beta prime, but the book calls beta. Because for the book, beta for linear phase filters was defined in a different chapter than this, but it doesn't matter. So you have it for beta equals 0, beta equals 3, and beta equals 6. So for beta equals 0, it just reduces to a good old rectangular window. Beta equals 3, it's this guy, and beta equals 6 is this guy. Okay? By the way, while we are at it, what other application is it in communications that you worry about the shape of a function like that? Anybody had to worry about it, design something in the communication industry? Yeah. When you do, for example, let's say a CPM system, continuous phase modulation system, or even an amplitude modulation system, there's a basic pulse that you use for modulating your stuff and shaping the signals that you end up sending over the air. And you want to design those pulses to have nice characteristics so that the spectrum of the resulting modulated signal looks nice and compact, and it doesn't spill over beyond where it is and all those other things. And so people impose typically conditions like, oh, it has to go through 0 at the two ends, its derivative has to be smooth and nice, its derivative of derivative has to be nice. You impose certain nice conditions on the shape of your pulses so that the final modulated signal looks good. So this business of window design and signal processing has a dual, if you will, in communication theory, where people design pulses that are used for modulation so that the resulting signals have compact spectrum. And why do you want to have compact spectrum? Spectrum is a scarce resource. You don't want to spill over your signal. You want what you want in communication. What you want to maximize is called bits per second per hertz. For every hertz, you want to have a modulation scheme that packs as many bits per second as possible. And this guy Shannon, 50 or 60 years ago, came up with the upper bound of how much max is that you can pack. He didn't tell you how to do it. He derived a mathematical theorem that tells you what that limit is. And ever since then, we've been trying to achieve that under certain ideal conditions, of course. And the prime example of bits per second per hertz is what? That has improved. I mean, you guys are just witnessing it with your own eyes. when you were a kid and your parents had dial-up modems in their homes, dial-up modems in my era was, when I was in graduate school, I would say it was I'm really ashamed to say it. It was 600 bits per second. It was. And you know what I had to do is I had to save all my money as a graduate student so I can buy a $600 Rakel modem that could only do 600 bits or 1200 bits per second. I can't remember now. And then I'm sure you don't remember that because most of you probably weren't even born at that year. But then you must remember 28.8 modems, right? You have heard of it, right? You're not that young, right? And have you ever used it?
Yes.
Okay, good. So I'm talking to some people who have some overlap with my generation. And then 28 modem became what? 56 kilobits. And how did that happen? It's the same telephone line. We're packing twice as many bits per second in every hertz of it. And how do we do that? That and no, it's not really compression. Compression is before you hit that. It's equalization techniques. It's characterizing the characteristic of a channel, and then canceling it out. If it has weird ups and downs, if the frequency response to the channel has weird ups and downs, you want to undo that so that you can pack more bits per second per hertz. And over that same channel that comes to your telephone line at home now, what can you get now? DSL. And what rates can you get roughly? I mean, it depends where you are, how far away you are from the end office and all those other things, but what rates do you get now? Megabits. You're right. The bare minimum they guarantee these days, like SBC guarantees, is about 300 kilobits per second. But in reality, I know at my home I'm getting about a megabit and a half per second. And it's the same telephone line that when I just joined Berkeley in 1988 as a faculty member, I could only get 28.8. I'm in the same house. It's the same room. It's the same physical thing. It's the same wall that I plug into. Nothing has changed. It really hasn't. I mean, that's what's so amazing, and then that's why you get a perspective if you live long enough. You just don't just get gray hairs. You see things evolving. Yeah, Kerry. Well, the problem is that Shannon assumes a certain number of things, that the channel is Gaussian and the noise is Gaussian and this is linear. So we're pretty, if those assumptions are correct, we're pretty darn close to Shannon's limit. However, Shannon did this work 40 years ago, and by the way, in case you didn't know, because of this work, he got a faculty job at MIT, but then as soon as he got there, he started modeling the stock market, and obviously he failed. And so he wasn't in this business too long, even though he had this really seminal work. But nowadays, people have started questioning all of those assumptions for Shannon's limit and say, wait a second, we can even go beyond that because those assumptions he made don't hold true in a lot of practical systems. So like many other pieces, it's a pure theoretical piece of work. It's a theorem, and it has a randomized proof as to what is possible. It doesn't tell you how to get it, but it tells you what is possible. But we're very close. In many modulation communication systems, we're very, very close to it. And the beauty of Shannon's theorem is not that it tells you how to do it, but as long as you're really close, you don't go to bed sweating over and not sleeping, oh God, can I improve it more? Can I get closer? You're exactly how far away you are. And that's the beauty of any result that is provably optimum, you've proven under certain set of conditions is optimal, because you know how far away you're from the best thing. And so coming back to this example of, it's the same plug, the same wall, the same wire that comes to my house that's carrying now, 100 times more bits per second per hertz than it used to. So what has changed? Well, what has changed is that Alcatel modem that's sitting on top of my PC. And what is that modem doing? It's equalizing. It's equalizing that same line, trying to figure out what the frequency response of the channel. I mean, you can think of the line connecting the telephone office to my home as a channel. It has a frequency response, and it's not flat. It's got ups and downs. So that Alcatel modem is just equalizing, and that's why I can get so many bits per second per hertz. And what else is happening in the communication world, in the modulation world? What's happening there? you come up with very powerful, I think one of you said it, modulation schemes that packs more bits per second per hertz than it used to. We used to get off of our spectrum, we used to get 1 bits per second per hertz, and now you have much more mathematical modulation schemes that you can pack in 6 or 7. It involves much more complicated decoder at the other end, but guess what? We've got all these VLSI chips that can do that complicated mathematical dynamic programming decoding and get that 6 bits per second per hertz off of it. As an example, your satellite thing, the direct TV box that you have on top of your TV, that's doing a whole lot of demodulation of fancy signals. And how is FCC packing HDTV into just 6 megahertz? We used to have we still do analog TV channels that are 6 megahertz apart, right? But how are we packing that many bits of HDTV into it? Powerful modulation schemes. OFDMs and this and that and the other, for which there's a lot of contention. Everybody comes up with their own favorite modulation. Oh, mine is better. No, mine is better. I pack more bits per second per hertz. But the bottom line is it has improved over the years. And so you can pack in something like HDTV requires 17 or 18 megabits per second, and they just pack it in 6 megahertz. That means they can do about 3 bits per second per hertz over the spectrum, right? Okay, I got detoured again. Back on track here. So this shape design of these waveforms, besides windows in signal processing and filter design, has a lot of other sort of consequences in other fields as well. And people spend mathematicians essentially spend a lot of time designing functions that have desirable properties, both in time domain and in the frequency domain. And it's not an easy thing to do. Anyway, so these are the 3 Kaiser windows corresponding to the 3 different values of betas. And I'm trying to now convince you that the changing beta allows you to trade off between main lobe and side lobe. And here it is. This is the magnitude of the Fourier transform of those windows. And beta equals 0 is the solid line. So you can see it has a narrow main lobe, but very high side lobe. Beta equals 3 is dot dashed line. So it has a slightly higher main lobe, but also slightly lower side lobe than beta equals 0. And finally, beta equals 6 has what? Which one is that? I have to. My eyes don't. Oh yeah, I see this. This is beta equals 6. Okay, and it's got much lower side lobe than both of those, but it has a fatter main lobe. Okay. And just to convince you that changing m, the duration for a fixed beta, changing m doesn't change much. You can look at this picture if you can. Some of these things. You can look at this picture here. So m equals 10 is this solid line, m equals 20, and m equals 40 are these other ones. So as you change m, wow, the main lobe becomes narrower and narrower as m goes up, as you double it. But the side lobe, well, there is a change between 10 and 20, but between 20 and 40, there's not much of a difference. So the main mechanism to affect your side lobe, if you really want to have a knob, is through this beta guy in terms of Kaiser window. So, what I guess just to give you a comparison point between Kaiser and these traditional windows, I'll refer you back to this table 7.1 again, which not only has the peak side lobes and approximation width of these different windows, but it tells you the transition width of equivalent Kaiser window. That means what the equivalent Kaiser window, what kind of transition width would have, and you can see in almost all cases, the equivalent Kaiser window has of length m has a smaller transition width than these other guys. So that's why I said Kaiser came and ended that business. He essentially, what's the word? Not obviated. Yeah, he put these guys out of business, basically. His thing is better than theirs, and that was the end of that whole thing. But then a few years later, Parks and McClellan came up with what's called an optimum filter design, and he put all of these guys out of business. And the way you know that they got out of business is there was no more papers published on FR filter design. That's it. It was mid-1975. Jim McClellan did his PhD thesis at Rice with Tom Parks. And now McClellan is at Georgia Tech, Parks is at Cornell, but that's a different story. But that it put an end. That was the last word. Nobody ever said anything more on FR filter design. It's good. I mean, you closed it, the whole field. You solved it, and that's otherwise, there'll be like more research for years and years to come. So here we go on this thing here. So let me just wrap up then few. So besides the fact that Kaiser window has this nice beta, after Kaiser came out with it, he also came up with some rough guidelines for designing FR filters using his technique. And he says that here's so design using Kaiser's technique, Kaiser's window, if you will. So he said, if you call delta of omega to be delta sub s minus delta sub p, which we just call the transition width. First, I'm going to give you some notation, and then tell you what the result is. And then number two, if you call ripple in passband or stopband, just to be delta. And that's one of the weaknesses of Kaiser's design, is because you use the same delta for passband and stopband. There are some applications you can afford to have higher ripple in one than the other, but Kaiser just doesn't take that into account. It's just as a simplified method. And call A, this quantity A, to be minus 20 log 10 of delta. Then these are the parameters that you should choose for M and for beta for Kaiser window. Then you can choose alpha prime, which is the same as M, and beta prime as follows. And the way he came up with this thing that I'm going to write down is purely numerical simulations. He just kept designing a million of these and fit a curve. The good old method of, a lot of simulations. So his thing was, number one, choose M to be equal to, oh God, and now I'm, yeah, there's an issue here. M is equal to 2 alpha, which means that I made a mistake here on page here. This need not have been alpha prime. This is not alpha prime. That's the same alpha as we had before. And this is alpha is equal to 2m, not m. Okay? There's a typo there. No. Hold on. Oh, yeah, m is equal to 2 times alpha. So then it's given by a minus 8 over 2.285 delta of omega. Okay? And beta prime, furthermore, is given by another fancy equation. Well, I'm running out of space in this space, so I'll move on here. So beta prime is given by 0.1102 a minus 8.7. For a larger than 50, it's 0.5842 times a minus 21 to the power of 0.4 for a between 50 and 21, and it's 0 for a smaller than 21. That's why I said there's no derivation to it. It's all a numerical result. He just kept plotting this until the thing worked. Okay. So just to give, before the lecture ends, let's just give you an example of filter design using Kaiser's. Suppose I want to design a low-pass filter, and the specs are as follows. Omega p is 0.4 pi, and once again, this is the magnitude of my spec. This is omega p, omega s. Omega s is 0.6 pi. Delta p, which is how much ripple I can have here, it's 1 minus delta p, is 0.01. Delta s is 0.001, so I can have smaller ripple in the passband, but Mr. Kaiser doesn't take advantage of that. You have to put based on this, we have to pick this delta parameter, which goes into these equations, as the larger of the two, 0.01. Okay? And here we go. How do we, so compute, so we know what delta omega p and omega s is. Subtract these two things, you get delta omega. Delta omega is 0.2 pi. You plug that into, can you zoom out? Yeah. So you plug that into here, and what that tells you what your value of alpha is. And then you also know what your ripple is. Delta is 0.01. That means A, this other quantity coming back up here again, is minus 20 log 10 of delta. So minus 20 log 10 of delta. Okay, so that tells you what A is. And delta is 0.01. Log 10 of this is minus 2, so it's minus 40 dB. Okay, so you plug in, you have the value of A and you have the value of delta omega. You plug it into these two things, and it gives you candidate values for M and for beta prime. So you plug in to these two equations, and you get M and beta prime. And actually, I made a mistake here. One more mistake. If I have my ripple condition is 0.01 here and 0.001 here, if I pick it at 0.01, I'm going to have ripple of 0.01 here and 0.001 here. And is that acceptable? No, I won't satisfy the spec. Here, I'm supposed to have 0.001. So I have to choose the smaller of the two, not the larger of the two. So delta is 0.001. So that's minus 60 dB. Okay. You see why? Because the specs tells you this, the delta cannot exceed a certain value. So I have to pick the smaller of the two to do that. Anyway, if you go through this motion, what you get is M is equal to 37. That means the number of taps is 38. Okay. And what kind of filter is that? Well, we assume that we're going to have beta is equal to 0 to get our filter because we wanted to get either type 1 or type 2, and now we get an even number of taps, so it ends up being a type 2. Okay, so here, before we even got going down here, remember, you have to, this specs that you're given is just magnitude of h of omega. From that, you have to come up with h of omega. And to go from magnitude to just h of omega, you have to tell what the phase is. In other words, you start saying that, okay, now h sub d of omega is magnitude of h sub d of omega times some phase. And what phase am I going to choose? Well, generally speaking, is e to the j beta, e to the j alpha omega. Generally speaking, it's that, right? But what I'm going to do is I'm picking beta equals 0. Which means that I'm going to have type 1 or type 2 for my filter. And I plug into these things. After I get M and I get beta prime, then I go back to W of N and I compute my Kaiser window based on the values of M and beta prime that I found, and that gives me my window. Now I have to multiply the window by some H sub D of N, some ideal low-pass filter, right? And how do I get that ideal low-pass filter? It's the inverse DTFT of H sub D of omega. But what's H sub D of omega? It's the magnitude, some phases. So I have to make some assumptions about these phases before I can know what H sub D of omega is, before I can know what H sub D of N is, before I can multiply that H sub D of N by that window function, right? It's a ripple effect. So I have to assume something about this phase, and I'm assuming that its beta is equal to 0. And alpha is the same alpha as pops out in my design, right? It's the same. This alpha in the Kaiser filter here is related to the length of the filter as before. It's the same thing as pops out from these two equations. Okay. So here we go. And the fact that I assume beta is equal to 0 and ended up with a type 2 filter, have even number of taps, and I ended up with a type 2 filter, is that problematic? No, because a type 2 filter can easily do low pass filter. I could have been in an unfortunate, if I suppose I was designing a high pass filter, and I'd assume, let's say, beta is equal to 0, and accidentally plugging into these equations that Kaiser gave, I ended up with the wrong number of taps, even or odd, so that it ends up being a filter that cannot be a high-pass filter. Then I have to get myself out of it. Because Kaiser didn't care about linear phase, type 1, type 2, type 3, type 4. He's just giving you these two equations as guidelines of how to pick the various parameters for his window function so that it would work. But so what type filter you end up choosing and designing is your responsibility in some sense. So once Kaiser gives you the suggested value of m, then based on the assumptions that you made, you have to see whether the type is the correct one for what you wanted. And there's a good example of this in Oppenheim and Schaefer for designing a Kaiser high-pass filter where the value of m doesn't work. Actually, this particular value of m doesn't work either. Let me just show it to you why it doesn't. After you, so let's just, so you get this filter here. M is equal to, you solve it, beta becomes 5.6, m becomes that. This becomes your h of n and all those other things. And this is the example of your h of n, the filter that you ended up designing, the low-pass filter you ended up designing. It is type 2 because it has a symmetry like this. This is the magnitude of it. And this is the approximation error. This is the ripple in the passband, the deviation from 1. And this is the ripple in the stopband, the deviation from 0. And unfortunately, this number is 0.001. Unfortunately, here and here, this thing exceeds 0.001. So in some sense, this m equals 37 didn't satisfy the specs. It exceeded 0.001. So what do you do next? You increase m by 1. Make it m equals 38. And if you do that, I don't think there's a plot in this book, but if you do that, that just about makes it satisfy. And if you make m equals 38, you move from type 2 to type 1, right? But that's not a big deal because type 1 is a can-do-all. It can be any filter, so we still didn't run into any kind of a problem. But in some situations, let's say, again, it's in this example in Oppenheim and Schaefer, I encourage you to read it, example 7.9. You're designing a high-pass filter, you come up with these estimates that Kaiser gives you, and the number m that you got makes you have a type 2 high-pass filter, and we know there is no type 2 high-pass filter because type 2 has h at, the frequency response at pi equals 0, which ends up in a design like that, and that's no good. So then you should get yourself out of the type that doesn't satisfy that kind of a filter. Okay, I'm going to stop now. Pick up the solution, pick up the handout for, let me just give half the handout to this part of the class and half to the other. You guys pass it along, and half to this side.